So thank you very much for the introduction and for giving me the opportunity to give a talk at this school. So the title of my talk is An Introduction to Anabelian Geometry, and it will be, I would say, rather brief introduction. So I will just touch a few topics, so it's not very, so I won't cover that much. I will just concentrate on one specific thing. So here is the overview of this talk, and as I said, the goal will be to give a brief introduction, but not to general Anabelian geometry, but just to the Anabelian geometry of hyperbolic curves, and also only characteristic zero. So we'll only deal with this particular case. And we'll start by recalling some basic definitions that actually have already appeared in the previous talk, and then we'll state what is the Grothendieck conjecture in Anabelian geometry. So this will be, roughly speaking, the first part of this talk. In the second part, I will actually sketch a proof of certain theorem of certain group theoretic construction, which is described here as a reconstruction of a function field, but more precise statement will appear later. Right, so let me start. So this is a brief, just to recall briefly the definition of the Étale fundamental group of a scheme. So one starts with a connected scheme and considers a category of schemes which are finite étale over X. Then we choose a geometric point, which is a sort of base point, which determines a fiber functor. So this is a functor from the category of schemes étale over X to the category of finite sets, defined by mapping this scheme Y over X to the underlying set of a geometric fiber, the fiber over X. So this is just a finite set. And then there's the Étale fundamental group with respect of X with respect to this base point is defined to be the automorphism group of this functor. So this definition has already appeared in the first talk of today's. Right. So clearly from the definition we have this inclusion. So and using this product, this will naturally give this Étale fundamental group profinite topology. So it will be not only a group, but it's actually a profinite group. And moreover, essentially by definition of phi x, this functor, fiber functor, will factor through the category of finite sets equipped with an action of Étale fundamental group. So we'll have this functor, this enhanced functor. And in fact, this will be an equivalence of categories. So that was also mentioned previously. And also note that this construction, it's functorial with respect to morphism of schemes, at least if we specify the base point. Right, so that's the definition. I think I have some examples here that is useful to keep in mind. So first example is the very basic one. If the scheme is just a spectrum of a field, and our base point is again spectrum of an algebraic closure of K, then basically by definition one easily checks that the construction of the Étale fundamental group is the same as the construction of the absolute Galois group of K with respect to this algebraic closure. So that's one of it basically shows that this is a right generalization of Galois theory, because it gives the same answer for points for spectra of field. And the second example is slightly more general. We consider X is normal integral. Let us write this notation K of X to be the function field of X, and let's choose let us write X to be a generic point of X and X bar to be a geometric point determined by some algebraic closure of a function field of X. And then we have this sequence of morphism of schemes from X bar to X to capital X. This will determine the surjection from the Galois group of the function field to the Étale fundamental group, which is actually surjective. So in other words, the Étale fundamental group is some quotient of the absolute Galois group of a function field. And so this quotient is relatively easy to explain. It's a quotient which corresponds to those field extensions such that if we normalize X in this field extension, that it's still normalized. That it's still unramified over X. So this is another way to think about Étale fundamental groups, at least in the normal and integral case. So this is just some quotient of a Galois group of a function field. And the last example is of an abelian variety. When our base field is algebraically closed, then one has actually a natural isomorphism between the Étale fundamental group and the Tate module of A. And I also skip the base point in this notation. Basically, that is thanks to the next remark, which says that actually, whenever we choose two different base points, X bar and X bar prime, in fact, these two functors are isomorphic, but no, this isomorphism is not unique. Therefore, the Étale fundamental group with respect to two different base points, these two groups are also isomorphic. But this isomorphism, again, it's not unique. It's unique up to conjugation. So this is the dependence on a base point, basically. Right. So from now on, we'll only consider smooth varieties of a fixed field K of characteristic 0, and we'll skip base points from the notation, and we'll use to ease notation, we'll write pi of X to be the Étale fundamental group of X. And also the second notation is delta of X. This will be the Étale fundamental group of the base change of X to some fixed algebraic closure. So this is basically just to have an easy notation. And also GK will be the absolute Galois group of K, of the base field K. Right, so in this setup, we have the following short exact sequence, which is called sometimes fundamental exact sequence. So we have a natural map from the geometric fundamental group, so delta X to the Étale fundamental group pi X, which is injective, and the quotient is mapped to it's isomorphically mapped to the absolute Galois group of the base field K. And this sequence is induced from this sequence of morphism. So if you forget about this dependence on base points, you may think of this construction of the Étale fundamental group as a functorial construction. So this sequence of morphism of schemes will produce this short exact sequence of fundamental groups. And also let me note that in this from this short exact sequence, one obtains this representation from GK, from the absolute Galois group of K, to the outer automorphism of delta X. So this is also a construction that has appeared in previous talk. But actually, in this talk we will not discuss this problem, because one feature of Anabelian geometry is to consider this map. Is it injective or not? And if it's injective, then how you can characterize the image of GK. So actually, this topic is a very interesting topic, but they will not discuss this issue. We'll concentrate on something else. Right. So we suppose further that X is actually a curve. So we further specialize. We'll write X CPT for the smooth compactification of X, and GR will stand for genus and the number of cusps. So what I refer to as a cusp is always a geometric point on the boundary of this compactification. So this is a common usage of the word cusp in this context. And we say that X is hyperbolic if the following inequality holds. So this is basically removing certain small amount of non-interesting cases, let's say. Right, so there was already mentioned in previous talks what is the relation to topology. So let me also say something about this. So let SGR be a surface of genus G. So this is a compact surface of genus G with R punctures. And we will write this gamma GR for the topological fundamental group of this surface. And then, thanks to this characteristic zero assumption, one knows what is the structure of delta X. So the structure of delta X basically that it is isomorphic to the profinite completion of this surface group. So this was already also mentioned, that we have a certain equivalence of let's say algebraic covers with analytic covers. And also maybe to have a better picture in what is the structure of this gamma group. So there is a well-known, from topology, there is a well-known presentation of this group as a quotient of a free group generated by 2G plus R elements with respect to one well-known relation. So here, this Ci, they correspond to loops around the punctures, and AI and Bi are some sort of standard loops on the torus. And also note that X is hyperbolic if and only if this group is non-abelian. And maybe I should say at this point what's the meaning of anabelian. So anabelian essentially means that something is very far from being abelian. So it's the opposite of being abelian. And if you look at this group, this gamma GR, this is usually even a free profinite group. If G is greater than 1 and number of cusps is at least 1, then in fact you have a free profinite group. So it's something very non-abelian. So that's basically the meaning of anabelian. And so what are the let's say anabelian conjectures? So the general philosophy for this abelian is that for certain class of schemes that we call anabelian, one should be able to, in some sense, reconstruct this scheme, this variety, from its fundamental group. So this is basically what we should consider when we should consider X as an abelian scheme. And also, at least in dimension 1, we know what it should be. It should contain hyperbolic curves. They should be anabelian. So that is the general philosophy. More precisely, one can ask whether this, if you think of constructing Talton group as a functor, so you may basically ask whether the functor is full and faithful. And if you ask this question, then you may actually try formulate this versions of Anabelian Grothendieck conjecture. So I will denote it by GC. So there are more versions, but here we will consider just two. One is isom GC, which says that the following map should be a bijection. Of course, that's the assumption that x, y, and x2 are Anabelian in this in the sense. So what is this map? Is between k isomorphism of varieties between x1 and x2, and this is what is this isom out? So this is this stands for outer. Right, so outer here means up to conjugation by this delta 2, because we'll assume that this isomorphism they are over GK. So if you remember, we had this fundamental exact sequence. So we've seen that pi x surjects onto GK. So you may consider maps, in particular isomorphisms between pi 1 and pi 2, which are compatible with this surjection. So this is the meaning. And so this is, let's say, the isom version, and there is also a hom version, so which is basically the same, but we consider only homomorphism. But also there are some adjectives, additional adjectives that you have to add. So on the level of maps of varieties, we add this dom, which stands for dominant, and at the level of profinite groups, we add open. So this basically means that this map should be open as a map of topological groups. So these two statements, they are usually referred to as Anabelian Grothendieck conjecture, either isom form or hom form. Right. So what is known about this conjecture is so I will mention just this three results. So this is the development that was done in the 90s. So first of all, Tamagawa proved this isomorphic version of Grothendieck conjecture for affine hyperbolic curves over a number field. So in other words, one can say that this was a proof that this Grothendieck intuition that hyperbolic curves should be Anabelian was right. And also, and he deduced this result from a certain version of the final fields. Later, or more or less about the same time, Wojciech proved also isomorphic version of Grothendieck conjecture, this time for proper hyperbolic curves. So complementing the work of Tamagawa, again over a number field, and that was done again by applying some method over finite fields, which was previously done by Tamagawa. And finally, the strongest result in this context is a version of hom Grothendieck conjecture. So not only isomorphism, but only certain homomorphism. And for all hyperbolic curves, and for much more general class of base fields, that are called sub-p-adic fields. So being sub-p-adic means that a field can be embedded in a finite extension of some QP. In particular, every number field and every p-adic field is sub-p-adic. So these two base fields that are quite often used, they are covered by this theorem. Right. So it is actually this last the last bullet point that we are going to use. So maybe what you have to remember is that this home version of Grothendieck conjecture is true for number fields. So this is all that we are going to use. Right. So it was already briefly discussed in the previous talk. And actually, in Anabelian geometry, we often consider two types of questions. So one is with sometimes called bi-Anabelian. So then the question is, if you are given, for example, two schemes X and Y and morphism or maybe an isomorphism between the fundamental groups, does it follow that this morphism or isomorphism is induced by certain morphism of schemes? So this is what we mean by bi-Anabelian. In other words, there are two schemes, there are two fundamental groups, and we basically ask the question of certain whether a certain functor is full, or maybe whether it's faithful. If we are interested in the uniqueness of this map of schemes. So these problems of this type are called bi-Anabelian. And there is another type of a problem called Mono-anabelian. So mono stands for one. So we only have a one fundamental group of one scheme, so pi x. And we are interested in reconstructing certain information of this scheme from this topological group. So maybe even this is maybe it's even closer, this approach Mono-anabelian to maybe what Grothendieck had in mind, because in some sense this is sort of reconstructing a scheme from of its fundamental group. And we usually have an implication that Mono-anabelian result implies a bi-Anabelian result by some functoriality argument. So in some sense, you may think of Mono-anabelian result as a little bit stronger. And actually, in the rest of this talk, so I will try to give a sketch of a certain Mono-anabelian result. Namely, we'll sketch a construction of a function field of a hyperbolic curve or number field from its Étale fundamental group pi x under some assumptions. So I will state what we are going to do. I will state it more precisely on the next slide. Right, so we'll sketch the proof of the following theorem. So we start from a hyperbolic curve of a number field, and we have this notation for the function field of a base change of x to a direct closure of k, and as before we have pi x, the Étale fundamental group of x, and moreover there is some additional assumption. So we assume that the curve x is isogenous to a hyperbolic curve of genus 0. So I will explain this assumption later. So just remember that there is some additional geometric assumption, and then we claim that there exists a sort of functorial group theoretic algorithm for reconstructing this function field of the of x base change to k bar equipped with an action of gk, and this reconstruction it's a reconstruction from this topological group pi x, so from the Étale fundamental group of x. Right. So so we have, I think, 35 minutes, so I should be able to cover the sketch of this theorem. So here is the plan, how we are going to do this. So to reconstruct this k bar x, I will try to briefly discuss the following. So I will first I will discuss how certain geometric operations such as Étale curve or Galois-Étale quotient can be expressed during the fundamental group. So in other words, how to think of this operation group theoretically. Another next step will be applying the first bullet point to construct from the fundamental group of X to construct a fundamental group of an open subscheme of X. So this is some non-trivial task, and it's in some sense the most crucial step in the whole construction. Here is where we use this additional assumption. And the last two bullet points are not maybe that difficult. So one is we will use Kummer theory first to embed Kx cross inside certain cohomology group. So this will be a reconstruction of a first multiplicative structure of the function field, and then in the last bullet points we'll apply certain classical argument of Uchida to reconstruct the additive structure. So that's basically the plan. So let me go further. So before we start, so we need to observe some basic fact that if that actually this short exact sequence can be already constructed from this topological group phi of X. So the reason is that you just need to characterize what is delta X inside of phi of X, and we've seen the we've seen the structure of delta of X, that this is a certain finite completion of a certain topological fundamental group. In particular, it's topologically finitely generated, and moreover, it's also closed and normal. And in fact, one has to realize that this is the delta X is in fact the maximal subgroup of phi X, which has this three properties. So this is true for. I mean, this argument is correct if K is if our base field is a number field. If K was a mixed characteristic local field, then the statement that we can reconstruct delta of X is still true, but you have to use a different argument. Right, but nevertheless, in the following we'll freely use phi X and delta X. In the construction, we will treat delta X as reconstructed from phi X, and also we'll use this G of K, but you should think of G of K as basically as this quotient. Right, so I need to discuss a certain notion which is called the inertia group of cusps. So cusp was a geometric point lying on the boundary. So for every cusp, we have an inertia group inside the geometric fundamental group delta X, which is a subgroup well defined up to conjugation, which is isomorphic to Z hat. So you should think of inertia. I'm not going to give a precise definitions, but you should think of the inertia group as a measure of ramification of a cover over this point X, and also write dx for the normalizer of inertia inside phi of X. So, and this dx is called the decomposition group of X. And then, if we assume that this cusp is K rational, we have again the following short exact sequence. So I of X is inside delta of X, and dx is inside phi of X. And this actually determines an action of Galois group on phi of X. And one knows that this is basically given by the sexatomic character, and we have actually a canonical isomorphism between I of X and Z hat 1. Right. So this is so in other words, to every summarizing, to every cusp of X, we have associated a conjugacy class of inertia groups. So how do we use them? So observe that if we have the following situation, that we have some X prime, which is let's say between X and X compactification, such that this X prime is just adding one point, adding one cusp. So this is what I will refer to as partial compactification. So if you think of compactification as adding points to an affine curve to make it proper, then partial compactification will be adding just some points. Maybe partial compactification is not necessarily compact. Right. So if you have this partial compactification X prime, then this open immersion X inside X prime will induce actually a surjection of Étale fundamental group. So in other words, pi X prime is a quotient of pi of X, and the kernel is generated by the conjugacy class of inertia group of X. So in other words, you obtain pi X prime by killing the inertia at X. So this is maybe what you can remember. Right, so inertia groups play a very important role, and it's useful to know how to reconstruct them. Useful to know how to determine which subgroup is an inertia subgroup inside delta of X. And in the number field case, there is a certain criterion due to Nakamura, how these subgroups are characterized. So it's done in the following way. So we introduce that the following, if J is a subgroup of delta of X, which we assume that is procyclic, so it's isomorphic to the hat. Let's say that it's of cyclotomic type if it satisfies the following two conditions. So one is that the normalizer of J in pi of X will surject onto an open subgroup of the Galois group. And the second bullet point is that the induced action of this GK prime on J is given by the cyclotomic character. So from the previous slide, you maybe remember that actually inertia group satisfies these two bullet points. And the criterion of Nakamura at least says that this is the only characterization that already these two assumptions, they implied our subgroup is inertia subgroup. So in other words, inertia subgroup of a cusp is the same as a maximal procyclic group of cyclotomic type. Right, so we say we won't say anything about the proof except that it uses certain Frobenius weight argument. So you don't really need to remember this definition from this slide. So the only important point is to remember that the inertia group of cusp can be group theoretically determined inside delta of X. So there is a certain characterization. Right. So so recall that on our assumption, so K, base field K is a number field, and we only consider hyperbolic curves. So we know that this homomorphic version of Grothendieck conjecture holds. You actually will use it. So it is needed to make this construction, to make sure that this construction makes sense. And then I mentioned at the beginning that certain geometric operations that we need to, in some sense, describe them group theoretically. So how it is done? So the first one I will call the cuspidalization. So what does it mean? So if you have X prime, that is a partial compactification of X. So in the sense of, as I defined 2 slides before, so if we have this partial compactification, then we've seen that we have a quotient from Étale fundamental group of X to pi of X prime, and we claim that this quotient can be actually reconstructed from the group pi of X. And this follows from the characterization of inertia group. So basically, to go from X to X prime, you have to kill inertia at the cusp. So in other words, you are decreasing the number of cusps. So that's the reason we, let's say, call it decuspidalization. So this is going from X to X prime. So it can be done group theoretically in the sense that the Étale fundamental group of X prime can be reconstructed naturally from the Étale fundamental group of X. So the next second geometric operation is very easy, because this is basically from the definition of Étale fundamental group. If this time X prime is a certain finite Étale cover, then we know how to describe, how to reconstruct the Étale fundamental group of X prime from the Étale fundamental group of X. because this is simply a certain subgroup of pi of x. So, and this just follows from the definition of Étale fundamental groups. So this step is easy. And there is also a third step that we can actually construct not only finite Étale covers, but also finite Étale quotients. So there, basically, it follows from the fact that the quotients in a category, that if you have a category that basically you may add certain objects to this category, let's say category theoretically, and they will correspond to certain quotients. And right, so let me just remark that in these 3 bullet points, we actually need this home version of Grothendieck conjecture to, in some sense, to construct various fundamental group of curves, so that we can talk about the morphism between these fundamental groups over K. This is how we need to have this homomorphic version of Grothendieck conjecture in various of these reconstructions. Right, but our goal is actually to construct not decuspidalization, but cuspidalization. So it is a certain construction that we want to go from x to x prime, and this time x prime is an open subscheme of x. So in other words, we want to construct from pi of x, we want to construct the extension pi x of prime. So this is a certain larger group which will surject onto pi of x. And this is, let's say, the most non-trivial part of this, from this family of geometric constructions. And it is here where we need certain additional assumptions. So this construction is called Belyi cuspidalization. So the name Belyi already appeared in the first talk. So we need to assume that our curve x is isogynous to a hyperbolic curve of genus 0. So what does it mean? It means that there exists the following diagram, where y is a hyperbolic curve, p is a hyperbolic curve of genus 0, and both these arrows are Étale. So this is the meaning of being isogynous to a hyperbolic curve of genus 0. And moreover, recall the theorem of Belyi, the famous theorem of Belyi, that informally one can say that the curve is defined over a number field if and only if one can find a morphism from x to p1, which is ramified over at most 3 points. And how we are going to use this theorem is in the following way. Suppose now that U is an open subscheme of x. So we would like to start from pi1 of x and somehow construct pi1 of U. So first of all, using Belyi theorem and our assumption, we will construct the following diagram. So if you look at the left part of this diagram, I hope you can see my cursor. So this follows from the assumption that from x we have this cover of y, which is finite Étale. Y over p is a certain Galois cover, and p is an open subscheme of p1 minus 3 points. So this is basically our assumption of being isogynous to a hyperbolic curve of genus 0. And by Belyi theorem, we obtain this part of the diagram, because we know that U is in particular, U is a curve defined over a number field. So there exists a certain map from U to P1, which is ramified over at most 3 points. So let's say these 3 points are 0, 1, and infinity. If we remove the preimages of these points, we obtain a finite Étale map from certain open subscheme of U to P1 minus 3 points. And observe now that if we start from here, so if we start from x in the bottom, and we want to go to U, which is at the top on the right, we and we go through these arrows, basically it only involves the operations that we have already discussed. So it's going up by finite Étale map, and then taking Galois quotient, then taking the cuspidalization, then once again going up by a finite Étale map, and so on. So in other words, if we start from pi x at the bottom and we perform these group theoretic operations, we may arrive at pi u, and also pi u we may once again perform this cuspidalization to pi of x, and then if you identify this group pi of x with the pi of x that we started with, which is allowed thanks to this Grothendieck conjecture that we assume, we may construct this surjection, this extension from pi u to pi of x. And let me also mention that this construction also produces something more. It also gives you the composition group of all rational points on x. So what is the composition group of a rational point? So a rational point on x will produce a section from the Galois group to the Étale fundamental group, and the image of this image of the Galois group is, you may think of it as the composition group. So you may take this as a definition of the composition group. But this will be useful later, this knowing that we also have this data of the composition groups of rational points. Right, so that's basically the end of this geometric construction. So summarizing, we can summarizing it, I would say that we can perform various constructions. In particular, the most importantly, we can reconstruct from pi of x pi of u, where u is a certain, where u is an open subscheme. We can do this for every open subscheme of x. Right. So so we have 15 minutes. So maybe I will certain parts that are maybe not that important, maybe I will discuss only briefly. Right, so I mentioned that we can construct these decomposition groups of rational points on x. So they are certain subgroups of pi of x. And in particular, we may talk about divisors. So if we have points, we may formally talk about divisors. And one thing that I have to mention is that we can characterize principal divisors among all the other divisors. So I will just briefly mention how it's done. If we have a section corresponding to a certain point, a rational point, one can. So first of all, if you have pi of x, you also have pi of j, where j is a Jacobian of x. So this is relatively easy. And then if you compose this section with the surjection from pi of x to pi of j, which is group theoretical, you may obtain a section that I call SP-ab. And then basically by considering, let's say, formal sums of sections and apply Abel-Jacobi theorem, one can characterize which principal divisors, which divisors are principal divisors among all divisors with zero. So maybe this is not that interesting, but it's relatively easy. And so far we've discussed about some geometric operations, but how we actually approach this construction of a function field x from its Étale fundamental group. So this uses Kummer theory in the following way. So one has the standard Kummer sequence, which will give us the boundary map from the regular functions, which are units, to a certain cohomology group. So which will be, so this is h1 of pi of x with coefficients with z hat 1. And so this map is injection, and So it makes sense to ask how can we characterize the image of this map inside this H1. So the image of a regular function inside H1 is usually called a Kummer class. So we would like to characterize Kummer classes inside H1 phi of x with coefficients in Z1. And the way it is done is once again by with the help of inertia subgroup. So if we have a cusp x, write I of x for its inertia group. So recall that we had this canonical isomorphism between I of x and z of 1. And then if we restrict elements from H1 of phi of x to various subgroups, various inertia subgroups, we obtain the following commutative diagram. So here there are some direct sums. They are indexed by the set of cusps. So basically we consider this restriction to all cusps. And then this direct sum of H1 of I x, this will be canonically isomorphic to z hat, the direct product of z hat. And inside of this direct product of z hat, we have a direct product of z. And actually, this is the part that we're interested in because this will correspond exactly to orders of zeros and poles of rational functions through the map div. So this is just taking divisor. And what we can gain from this diagram is that actually by taking preimage of the principal divisors. So principal divisors, if you think of them as living inside of this direct product of Z. Right, and also maybe I should mention this is just principal divisors supported on the set of cusps. So we only consider functions that have zeros or poles at the set of cusps. So when I say regular functions, so it usually should be regular functions without zeros, so units, but I hope it's clear for the notation. So once again, the result is that we can actually reconstruct this OX cross inside of H1. However, there is a certain still issue that has to be resolved is that these functions are actually multiplied by certain actually by profinite completion of K cross. So it's something that we need to remove. In other words, we want to descend from these functions up to K cross hat to functions up to K cross. So how it is done is by using another technique which is called evaluation. So if you pick some point P, a K rational point on X, and let SP be a section corresponding to this point, then once again we have the following commutative diagram. And the horizontal arrow at the bottom is just evaluating function at the point P, and the other horizontal arrow is just restricting the cohomology class through the section SP. And if we consider this restriction as a evaluation, because it is basically sort of group theoretic evaluation, we can see that the property that a certain function has a value 1 at a certain point, it's in fact group theoretic because it's basically vanishing of a certain map to vanishing of a certain restriction map. And in fact, this will be enough to reduce this indeterminacy from K cross hat to K cross, basically by evaluating functions at rational points. Right, so maybe I don't have that much time to go into details, but let's so In other words, you have to trust me that having this property is enough to reduce this indeterminacy. And also note that if you already know what are the regular functions, the unit regular functions, then you may actually also, in some sense, construct as its values this k cross inside k cross hat. Because a priori, if you look at this k cross hat, this as an h1 of gk, there is no. It's not clear how to distinguish from k cross. How to distinguish elements from k cross inside this h1. But this also can be done through this evaluation. Right, so here I have some technical remarks that maybe they are not that important at this moment. They basically say that the construction is a little bit more complicated, and I somehow simplified it to make it more to make it easier to present. But basically, these remarks. So you may read them after the talk because the slides will be uploaded to Slack. Basically, they say that the construction is a bit more involved, but I simplified somehow to make it easier. Right. So as a summary, so what we have shown so far is how to construct the group of OX cross from the fundamental group pi of X. And moreover, earlier we've seen that using Belyi cuspidalization we may reconstruct this extension. So from pi of X we may reconstruct pi of U, where U is an open subscheme of X. We can do it for every open subscheme of X. And therefore, if we apply the same construction to U, we may obtain the group of regular functions on U. Unit regular functions, and if we take the co-limit of all open subschemes, we'll essentially obtain the group of rational functions on non-zero rational functions, and this will also be naturally equipped with an action of gk, basically by, let's say, by factoriality of our construction. Right. So this is a brief summary of what we have done so far. And also recall that, as I mentioned, this property that the function has value 1 at certain point is also group theoretic. This is this construction that you restrict homology class of a function to a certain through a certain section, and then basically we check if the result vanishes. So how can we extend this to add the additive structure on this field? Because so far, what we've done is just having non-zero rational functions and only multiplicative structure. So the last step is actually the most classical and the most elementary one. It's usually statements of this form are called Uchita's lemma, where you have a field with multiplicative structure together with some additional data, and you want to reconstruct the additive structure. So the version that we are using here is the following. So we assume that X is proper, and basically there's algebraically closed, and this lemma will actually solve our last bullet point that we had in our plan of our talk. So this lemma says that if we are given the multiplicative group of non-zero rational functions together with a set of valuation maps. So what are these valuation maps? This is basically taking order of a function, order of its zero or a pole. These are just zeros. This only corresponds to zeros and poles. And the third bullet point is that for each valuation, so in other words, for each point, we also have a subgroup. We also have a specified subgroup inside the rational functions. UV of functions which actually have value 1 at this point x. And this is also group theoretic, as I mentioned previously. So if you have these three types of data, then actually this is already enough to reconstruct the additive structure on the set. So obviously we have to add 0, and this will functorially correspond to the additive structure on the field of rational functions. So this last step is actually very elementary, and maybe I will actually skip this. I will only show you that this is 2 slides. This is the first slide, and this is the second slide. It's elementary. It uses only some classical theory of linear systems. So even if you want, you may try to solve this as an exercise. It's not that difficult. But the point is that this lemma is actually enough to finish the construction, to add the additive structure to what we have constructed so far. And this is in fact the last slide of my talk. What I have still here is so maybe I would just briefly mention what are the references. So this construction follows actually construction from section 1 of the following paper of Mochizuki, Topics in Absolute Angular Geometry 3. And I also added some other references to some of the results that I mentioned. So 2 papers of Mochizuki are 2 papers related to Grothendieck Anabelian conjecture. Paper of Nakamura is where this criterion for inertia group was presented, and there are also papers of Tamagawa and Uchida. So Tamagawa is this first result about affine curves, about Grothendieck conjecture for affine curves over a number field, and there is also a very classical paper of Uchida in which this type of argument appears, where you in some sense reconstruct the additive structure of a certain field from its multiplicative structure together with some additional data. Right, so I think this is the end of my talk, and yeah, so thank you for your attention.